Hello everyone and welcome to this online lecture. My name is Patty Kokish. I teach math both in person and online at Ivy Tech. I teach in the Northwest region at Valparaiso and Michigan City. Today we're going to be doing topics from chapter 5, which is week 9 of Math 136 online. You just took your midterm last week, so if you didn't do as well as you had hoped, hopefully you're tuning in to watch these lectures so that you'll get a little bit of additional information. There's a lot of material to cover. I'm going to walk through a little bit of everything with some examples. If you have any questions afterwards, you're welcome to email me. My email is pseeburger@ivytech.edu. And you can also just find me by searching for Patricia Kokish as an instructor on Ivy Tech's website. So we are going to start with section 5.1, which is polynomial functions and models. So the first thing we're going to do is to identify polynomial functions and their degree. So a polynomial looks something like this, where basically what you have is you have numbers multiplied by x to some power, and then all of those things are going to be either added together or subtracted possibly. And a couple of important things is that the powers cannot be negative, okay? And they have to be integers. So they have to be non-negative integers. And then the other important thing to note is that the domain is going to be the set of all real numbers. So meaning that you can plug whatever you want in for x, and you're going to get some value out for y. Okay, so what we're going to do first is look at some of these examples and decide whether or not these are polynomial functions. If they are polynomial functions, we're going to state the degree, and if they're not, we're going to tell why they're not. So let's start with A, which is f of x equals 3x minus 4x cubed plus 8, or plus x to the 8th. And if we look at this one, this should be a polynomial, because what we have is we have numbers multiplied by x to some power, and they're all either added or subtracted together. We have non-negative integers as our exponents, so that's good news. So this is going to be a polynomial. The degree is going to be 8, so it's always the highest power of your x. Now if we look at B, if we look at the numerator, x squared plus 3, that is actually a polynomial of degree 2. And if we look at our denominator, x minus 1, that's actually a polynomial of degree 1. But together, when we divide them, they're not going to be a polynomial. It's going to be something called a rational function, which we're going to talk about in just a little bit. But g is not actually a polynomial function. It's the ratio of two distinct polynomials. All right, if we look down at C, that's h of x equals 5. This one is going to be a polynomial function. The degree is actually going to be 0. So if you think about it, you can write this as 5 times x to the 0 power, because anything to the 0 power is just going to be 1. So really you just have 5 times 1, which is just 5. So this is a polynomial. The degree is going to be 0, though. Now, if we look at D, this one's a little hard to see what the degree might be. So the easiest thing to do with this one is going to be to actually multiply it out. So if you actually FOIL this, combine like terms, you're going to get x squared minus x minus 6. So what you can see from that is that the degree is actually going to be 2. That's the highest power that you have for your x. Now this one down here, we have g of x equals 3x minus 4 times x to the negative first. Now, if you remember what we talked about with exponents, the exponents have to be non-negative integers. So this one creates a problem because we actually have a negative integer. So this one is not going to be a polynomial function because the second term, the 4x to the negative first power, does not have a non-negative integer exponent. Now, if we look at f, we have h of x equals 1/2 x cubed minus 2/3 x squared plus 1/4 x. So this has a lot of fractions. It looks kind of ugly, but if we look at it, we have x to the third power, x squared, and x. Those are all fine. All those powers are non-negative integers, and the fractions are just in front of the x. They're just multiplied, so that's not a big deal either. So this one actually is a polynomial. The degree is 3 because the highest power that we have is actually a 3. Okay, so to summarize this, these are kind of the ones that you should be familiar with just based on other things that we've done in this class. But if we talk about something where we have no degree at all, that's going to be something where we have f of x or y equals 0. That's called the zero function. And if you think about the graph of y equals 0, that's actually just your x-axis. Now, if we think about something with degree 0, we actually talked about one like this. F of x equals 5 was the one that we did. But really, you can have f of x equals any real number. So you could have 5 or 10 or a million or negative 10,000. It doesn't really matter. That's just going to be a constant function. And if you think about what the graph of that looks like, it's just going to be a horizontal line that goes through the y-axis at your value a0, where a0 is just, or a naught is just whatever value you're talking about. So if you had like f of x equals 5, for example, that would go through the y-axis at 5. Now we also have polynomials that are of degree 1. So if you have something like f of x equals a1x plus a0, where a1 is not equal to 0, that's going to be something that's a linear function. And you should be familiar with that. It's going to be non-vertical, non-horizontal. It's going to be a line. The slope is going to be a1, and the y-intercept is going to be at a0. And then we also talk about things with degree of 2, which is going to be something where you have like an x squared term. That's going to be a quadratic function. So what we know from chapter 4 is that that's a parabola. It either opens up or down. It depends on the value in front of your x squared. There are obviously polynomials with higher degrees, and we will be dealing with those, but these are the ones that you should already be familiar with just based on what you already know. Okay, so on the top left here is a graph of a polynomial function. You'll notice that it's nice and smooth, it's continuous, so there aren't any big pieces missing, and it doesn't have any like rough corners or anything like that. But if you look on the bottom right, this is not the graph of a polynomial function. If you notice, there are a few things pointed out here. There's this corner here, there's something called a cusp. We also have these holes, like right here, and then we also have this gap where it has like a hole and another dot. So this cannot be the graph of a polynomial function for all of these reasons: the corner, the cusp, the gap, and the hole. Graphs of polynomial functions always have to look like something like the upper left does, where it's nice and smooth and continuous. Okay, we also want to talk about power functions. So power functions always look something like this, where you have y equals, or f of x equals, a times x to the power n. A is just going to be a real number, cannot equal 0, and n is greater than 0 and an integer, so it's a non-negative integer. So some examples of power functions would be like f of x equals 3x. Now what we already know is that that is degree 1. You could also have something like f of x equals negative 5x squared. That's going to be degree 2. You could have something like f of x equals 8x cubed. That's going to be degree 3. Or f of x equals negative 5x to the 4th. That would be degree 4. Okay, so when we're talking about power functions, the most important thing to note here is what all of these various functions look like. So if you think back to when we talked about the function y equals x squared, when we did our transformation section, I think it was all the way back in chapter 3. If you remember, x squared was a nice parabola. It opened up. Okay, now if you think about it, x to the 4th, x to the 6th, x to the 8th, they're all going to look very, very similar to x squared. They both go up on both sides. They're going to be U shapes. So anytime you have an even integer, so x to some even power, it is going to look like x squared. Now the things that are different about it are that they're more narrow, okay? So as the power gets larger, it's going to get more and more narrow. And then also as the power gets larger, it actually flattens out close to the origin. So there are a couple of nice rules about even integer power functions. So f is an even function, so that means that it's symmetric with respect to the y-axis. The domain is going to be the set of all real numbers, and then the range is going to be the set of non-negative real numbers. So ranges from 0 to infinity, including 0. The graph always contains 3 different points: negative 1, 1, 0, 0, and 1, 1. And then as the exponent n increases in magnitude, so as we have larger and larger exponents, the function actually increases more rapidly. But then, like I said, near the origin, it kind of flattens out and gets a little bit closer to the x-axis. We actually have really similar behaviors when we have odd exponents. So things like x cubed. You already know what x cubed looks like. That's given on the left here in the black, as the black line. And what you'll notice is that the blue line shows maybe like x to the 5th or x to the 7th, some other larger odd integer. And what you'll notice is that it grows more quickly down here and up here, but it's also flatter near the origin. So it's pretty much the same rules as even integers. So we know that if we have an odd exponent, like x cubed, x to the fifth, x to the seventh, they're all going to look kind of like x cubed. They're going to be odd functions, which we already know. That means they're symmetric with respect to the origin. Domain and range is actually all real numbers for both of those things. And then they also contain 3 points. They're a little bit different. We have -1, 0, 0, and 1, 1. And then as the exponent increases in magnitude, it's pretty much the same. The function increases more rapidly, but for values near the origin, it's a little flatter. Okay, so now that we know what all of these different power functions look like, we can actually use transformations to graph some of this stuff. So let's say we're given something like this. F of x equals 1 minus x to the fifth. So if you think about it, kind of the base graph that we're talking about here is x to the fifth. Now, if you think about 5 is an odd number, so it's going to look kind of like x cubed. So what you have here is something that looks very similar to x cubed. It's x to the fifth. And then what you want to notice is there's this negative out front. So if you remember anything about transformations, you might remember that when we multiply by the -1, that actually reflects around our x-axis. So what we've done is we take our y equals x to the fifth, which is all the way on the left, and we reflect it around our x-axis, so we kind of flip it upside down. And what we end up with is a picture that looks like this in the middle. And then if you remember this 1, this is outside of our function, so that's actually going to move it either up or down. 1 is positive, so it moves it up. So what we do is we take now our middle graph that has already been flipped around the x-axis, and we scoot it up 1, and that gives us our final transformation. All right, let's do one that looks like this. Let's say we have f of x equals 1/2 times x minus 1 to the fourth. So if you think about this one, your base graph is going to be x to the fourth power. Now x to the fourth power, that's even, so it's going to look something like x squared. So if you'll notice all the way on the left here, there's a picture of something that's supposed to be y equals x to the fourth. It looks just like x squared pretty much. It's going to be a little flatter near the origin, and it's going to grow a little more quickly. And then what you want to think about is this -1, that's kind of inside your function. So if you remember anything about transformations, hopefully you remember that that actually moves it to the right 1. So what we do is we pick up our x to the fourth picture and we scoot it to the right 1. And then this 1/2, that's the number that either compresses or stretches our graph. So what we're actually doing is we're multiplying by 1/2, which is compressing by a factor of 1/2. So we're actually making our graph a little shorter, a little more squished down. So it looks something like this all the way on the right. Okay, now let's talk about real zeros of a polynomial function, and then we're going to talk about something called multiplicity, which is new. So if a function f has a real number r, then f of r is equal to 0, and r is called the real zero. So as a consequence, we have kind of this list of equivalent statements. Basically, r is going to be a real zero. Real zero can be interchanged for the word x-intercept. So if you're talking about your graph of your function, r, your real zero, is going to actually be one of the x-intercepts. And then in addition to that, x minus r is going to be a factor, and r is going to be a solution to the equation of f of x equals 0. So all of these things are pretty much equivalent to saying that r is a real zero. Okay, so the first type of question we have under this premise is that we want to find a polynomial that's of degree 3 whose zeros are -4, -2, and 3. So what we want to do is we want to write something where we have f of x equals some number. We're going to talk about what this number a is. And then if you think about this for a minute, if -4 is a real zero, that means that x plus 4 has to be a factor, so it's always opposite. And if you think about this for just a second, if we took -4 and we plugged it into here, we would end up with 0, which is exactly what we want to have happen if we're talking about real zeros. And then if you think about -2, that's going to have a factor of x plus 2, so again, it's always opposite. And if you're thinking about 3, if you plug 3 in here, you're going to have 3 minus 3, which is 0. So x minus 3 is that third factor. Now, in my math lab, I think that they take the answer in kind of the factored form, so I believe that you can leave it like this first form, but I'm not 100% sure on that. So what they've done here is they've actually multiplied this out, so they FOILed the first two, and then multiplied that by x minus 3, again using FOIL, and they ended up with x cubed plus 3x squared minus 10x minus 24. And then you'll notice you have this a out front. A can really be any real number, but the easiest thing to do is to just let a equal 1. So if you think about how you're going to write your answer, if a is just 1, then you just have kind of this 1 outside of here that doesn't really do anything at all, so you really don't even need to write it. Okay, now we're going to do it kind of going backwards where they give us the function and then we have to list all the zeros and their multiplicities. So let's say we have f of x equals negative 2, that's the a in this case, times x minus 2 times x plus 1 cubed times x minus 3 to the 4th. So if you think about this, we set each piece equal to 0. So if we take x minus 2 and set that equal to 0, we should get 2. That's one of the zeros. Now multiplicity, that's something new. In order to find the multiplicity, all you have to do is you have to look at this 0 here, we have x minus 2, and you look at its exponent. Now if we look at the exponent, it has an exponent of just 1 because there's nothing there at all. So it's really just x minus 2 to the first power. So the 0 of 2 actually has a multiplicity of 1. If we look at this second piece, the 0 is going to be negative 1, because if we plug negative 1 in for x, this whole thing becomes 0. And the multiplicity is going to be the power, which in our case is 3. So negative 1 is a 0 of multiplicity of 3, because the exponent on the factor x plus 1 is 3. Now if we look at this last one, 3 is going to be the 0 from this one, and the multiplicity is 4, because that is the exponent. Okay. So let's go ahead and graph a polynomial using its x-intercepts. So let's say we have f of x equals x times x minus 3 squared. And the first thing we want to do is go ahead and find the x and y-intercepts of the graph, and then use those intercepts to create intervals, determine if our graph is going to be above or below the x-axis, and then plot some extra points so that we can connect it in kind of a logical way so that we end up with a nice, smooth, continuous curve just like we would like. So if we think about this, to find our x-intercepts, you remember you set y equal to 0. If we do that, we just end up using the zero product property, which tells us to set the first part equal to 0 and the second part equal to 0. So we get x equals 0 or x minus 3 squared equals 0. So you get two solutions, x equals 0 or x equals 3. So those are our real zeros. To find the y-intercept, we set x equal to 0, and if we do that, we just get 0 again. So what we want to do is we want to draw a number line and then label the important points on our number line, which are going to be our real zeros. So our real zeros in this case are 0 and 3. So we put those on our number line, and then what we do is we use those numbers to create an interval. So the interval all the way on the left is going to go from negative infinity up to 0, and then we have kind of this middle interval from 0 to 3, and then we have this right-hand interval from 3 to infinity. So those are going to be the actual intervals. And then what we would like to do is we'd like to pick a number in each of the intervals. So a nice number that's from negative infinity to 0 would be like a negative 1. That's a nice number that's in our interval. And then what we want to do is we want to take that negative 1 and plug it into our original equation. And if we do that, we should get negative 16. So since negative 16 is a negative number, that means we're going to be below our x-axis on this interval. And then the point on the graph can be written as negative 1, negative 16. Now we're going to do kind of a similar thing over here. We're going to pick a number between 0 and 3. In this case, it's 1. That's a really nice number. You can never actually pick your endpoints. It's really important to note that. You have to pick something that's between those 2 points. Now if we take 1 and we plug it in, we should get 4. 4 is a positive number, so we know we're going to be above our x-axis, and the point on our graph is going to be 1, 4. Now onto our last interval, we have from 3 to infinity. So a nice number that's in that interval would be 4. So what we do is we take it and we plug it into our original. So we plug our 4 in, and we get 4, which is above our x-axis, so our point is 4, 4. Now what we do is we take all of this information, we take our zeros, which are 0 and 3, and then we take some new points that we found, 1, 4, which is right here, and 4, 4, and then -1, -16, that's going to be all the way down here, but it's not labeled. And then what we do is we connect it in kind of a nice, smooth way so that we have our graph of our polynomial. Okay, now a couple of things about multiplicity. Right now, all we've done is just find multiplicity, but it can actually be helpful when you're graphing. So the important thing to note is that if you end up with an even multiplicity, your graph is going to touch. If you end up with an odd multiplicity, your graph is going to cross. So this is something that's typically difficult for students to remember, but there's a nice little mnemonic device. If you were just remember the movie E.T., you'll remember that even touches, okay, so E.T., even touches, and then you're just left over with odd and crosses, so those go together as well. Okay, we can also find behavior near a 0. So if we look back at this example, f of x equals x squared times x minus 2, if we want to know what the behavior looks like near the 0, 0, which is from this first part here, what we do is we take 0 and we substitute that in for x, except for the part of the equation that the 0 came from. So we're not going to substitute it in here, because if we do that, we're just going to get 0 for the whole thing, which is boring. So basically what we end up doing is we have f of x equals x squared, so that's left alone, times 0 minus 2. And if we go ahead and simplify that, we get negative 2x squared. So what we know is that near 0, our graph is going to look something like negative 2x squared. Now, if you remember negative 2x squared, that's actually just going to be a downward facing parabola. So it's going to look something like this on the bottom right, sorry. And if we go over to 0, what you'll see is you actually have something that looks like a little downward shaping parabola near 0. Now, if we want to know what the behavior looks like at the other 0, which in our case is 2, what we would do is we'd substitute 2 in for x, except for the part of the equation that 0 came from. So what we do is we have 2 squared times x minus 2, and if we multiply that through, we get 4 times x minus 2, or 4x minus 8. And if we think about the line 4x minus 8, it's just going to be a line with a positive slope that goes through 0, -8, right? So what we end up with is, if we look over at 2, it's going to look something like a straight line. So if you remember, over at 0, it looked like a downward shaping parabola. At 2, though, it looks like a line. Okay, now the multiplicity of a real 0, we already determined that it helps us decide if the graph crosses or touches there. The behavior of the near the real 0 also determines how the graph touches or crosses. So it kind of gets a little more specific, shows you exactly what it looks like right there. Now, there's also a theorem for turning points. This one's a pretty easy one, but basically what we say is that if the polynomial has degree n, then it has at most n minus 1 turning points. And conversely, if the graph has n minus 1 turning points, then the degree has to be at least n. So if we have something like f of x equals x minus 1 to the 4th, then we know that the graph has at most 4 minus 1 or 3 turning points. So what you do is you just take the degree and you subtract 1, and that gives you the maximum number of turning points. If you're looking at a graph, you kind of do it in the opposite direction. Okay. Now, we already talked about power functions, and the reason that we did this is not only just transformations, but they also help you determine n behavior. So they help you decide what your polynomial looks like at the extreme values. So what's going to happen is that if you arrange your polynomial so that it's in descending order, your power function for your polynomial is just going to be the very first term that you're left with. So if you think about power functions, we know if we have an even power function like x squared or x to the 4th, that's going to go up on both sides. So it's going to be a parabola that opens up. If we have something where we have an even power like x squared, but it's negative, so like we have negative x squared or negative x to the 8th, we know that that's going to open downward. So it's going to go down on both sides. And then similarly, if we have something like x cubed we know that that goes down on the left and up on the right. But if we have something like negative x cubed, it's going to be flipped around. So it actually goes up on the left and down on the right. So the first thing we want to do with this is, if we're given this equation, we have f of x equals x to the fourth plus 5x cubed plus 5x squared minus 5x minus 6. And what we would like to do is we'd like to determine which of these following graphs could possibly be the graph. So the first thing I want to look at is y-intercept, because that's an easy thing to find. So in order to find y-intercept, we set x equal to 0. So if we do that, if we set x equal to 0, we're going to get -6 for the y-intercept. Now, if you look across our graphs, this definitely has a positive y-intercept, so that one's no good. So it can't be that graph. And then if we keep going, we know that the degree is 4. So we know that the graph can turn at most 3 times, because 4 minus 1 gives you 3. Now, if you look over at C, that has 1, 2, 3, 4, 5 turning points, so that one cannot be it. And then in addition, we know what the end behavior should look like. So if you remember, power function is going to be this first term, which is, in our case, just x to the fourth. We know that x to the fourth actually looks like x squared, which is just a parabola that opens up. So we know we're going to have arrows that are going to go up on both sides. So up and then up. And if we look at this one's going down and then down, which is not what we want. Okay, so it has to be B. So here's a nice little summary. You can find this in your textbook as well. This talks about the degree being n, the graph being smooth and continuous. The maximum number of turning points is n minus 1. At a 0 of even multiplicity, it touches. That's ET, the movie ET. Odd is going to cross. Between the zeros, the graph is either going to be above or below the x-axis. And then the end behavior is going to look like whatever the power function is. Okay, so let's walk through one example of this. Let's say we have 2x plus 1 times x minus 3 squared. So step 1 is to determine the end behavior. So I'm going to go ahead and multiply everything through 2x plus 1 times x minus 3 squared. If we do that, we get 2x cubed minus 11x squared plus 12x plus 9. So we know that we have degree of 3. So we know that our power function is going to be something like 2x cubed. Okay, so if you think about what 2x cubed looks like, that's going to go down on the left and up on the right. We also want to find the x and y intercepts. I have full confidence that you guys can all do this. To find the y-intercept, we set x equal to 0 and we get 9. To find the x-intercepts, we set y equal to 0. So if we set this piece right here equal to 0, we get -1/2. If we set this piece right here equal to 0, we get +3. So those are our x-intercepts, or our real zeros. And then we want to determine the multiplicity. So we know that at -1/2, we're going to have a multiplicity of 1, because that's our power right here. And we know that at 3, we're going to have a multiplicity of 2. Now, if you remember, even touches. So at 3, the graph is going to touch. And at -1/2, the graph is going to cross, because that had an odd multiplicity. If we want to talk about maximum number of turning points, we know that the degree is 3, so we know that the graph can turn at most 2 times. And then we want to determine the behavior near each of the x-intercepts. This isn't as important for figuring out what your graph looks like. I'm going to kind of skip through that. Now we want to put all of this information together. So my suggestion is to first always plot your zeros. So we have a 0 at -1/2 and a 0 at 3. So we put those on there first. Then I would suggest putting your end behavior. So we know that it looks like 2x cubed, which is going to go down on the left and up on the right. So I would always suggest putting an arrow going down from that last 0 and an arrow going up from that first 0. Then go ahead and pick any other points that you have. So you have 0, 9 as another point. And then you want to think about touching and crossing. We know at 3 that it's even multiplicity, so it should touch, which is exactly what's happening. And we know that at -1/2, it's odd multiplicity, so it should cross. And that's what's happening as well. Okay, now I want to talk about some things from section 5.2, which is rational functions. So a rational function is just basically the ratio of two polynomials. So we're going to have a p of x and a q of x, and they're just two polynomials that are divided. But q cannot be the 0 polynomial, because we know that we can never divide by 0. We've already done some domain examples that are very similar, but basically what you need to do is you need to set your denominator not equal to 0, and then those are the values that you need to exclude. So, oops, skipped a little ahead there. So if we look at this one, x plus 5, if you set that not equal to 0, you're going to get x not equal to negative 5. So your domain is all numbers x such that x is not equal to negative 5. And then if we look at this one right here, we have 1 over x squared minus 4. This is the difference of two perfect squares. X squared minus 4 factors into x plus 4, x plus 2 times x minus 2. So we know that we need to exclude the numbers negative 2 and positive 2. So our domain is going to be x such that x is not equal to negative 2, x is not equal to positive 2. And then if we look at this one here, domain of x cubed over x squared plus 1. If you think about setting the denominator equal to 0, x squared plus 1 equals 0, that one's not going to factor, okay? That's an imaginary one, so that one's going to be all real numbers. And then if you think about this one right here, x squared minus 1 over x minus 1, that's going to be all numbers except x not equal to 1, because x minus 1 equals 0, you get x equals 1. So x such that x is not equal to 1. So it's important to note that r of x can be reduced to x plus 1, but that these two functions, x plus 1 and x squared minus 1 over x minus 1, are not equal since the domains are not the same. All right, so another kind of function to add to your list of functions that you should know is y equals 1 over x squared. And you can plot this just by picking some points. You might notice that this looks pretty similar to your reciprocal function, except you have a piece where they're both above the x-axis, whereas before you had one on the left down here. You can always pick points in order to figure this out, but it's going to look something like that. So as with any of the other base graphs, we can use transformations to graph some more interesting functions. So let's say we have r of x equals 1 over x minus 2 squared plus 1. So if we think about that for a minute, we start with y equals 1 over x squared. That's our base graph. And what we're going to do is we're going to shift it to the right 2. So we take it and we pick our points, pick them up and move them to the right 2. You'll notice we also have this new dotted line here. This is called an asymptote. In just a few minutes, we're going to go through how to find asymptotes. But the asymptote is normally at 0, so when you move your graph to the right, it moves with it. And then we also want to move up 1. So we take it and we move it up 1. You'll also notice you also have a horizontal asymptote, which also moves with your graph. So these are the technical definitions for horizontal and vertical asymptotes. Basically, they're the values that as you move to infinity or negative infinity, it's the values that y approaches, essentially. So if you're going on to calculus, you're going to learn a lot about limits, and that is exactly what this is. We also have vertical asymptotes. So those are the values that x approaches as we get closer and closer to the line. So if x is approaching either infinity, if y is approaching infinity or negative infinity, like this one down here, as x is getting closer and closer to some value c, then x equals c is going to be a vertical asymptote. We can also have oblique asymptotes, which we'll talk about in just a minute. So if we want to find vertical asymptotes, what you want to do is basically make sure that your function is in lowest terms and then set your denominator equal to 0, and that's going to give you your vertical asymptotes. So if we look at this one, we have r of x equals 5x squared over 3 plus x. What we want to do is set our denominator equal to 0. So we say 3 plus x equals 0. So we get x equals negative 3. We have another one here, x minus 3 over x plus 2 times x minus 2. So if we set our denominator equal to 0, we get x equals 2 and x equals negative 2. Those are both our vertical asymptotes. And if we look at this one here, we have f of x equals x minus 1 over x squared plus 5x plus 4. We would want to factor our denominator. It would factor into x plus 4 times x plus 1. So we would end up with two vertical asymptotes, one at x equals negative 4 and one at x equals negative 1. We also have rules for finding horizontal asymptotes or oblique asymptotes. So If the degree of the numerator is smaller than the degree of the denominator, then what we say is that the rational function is proper. If this is the case, if you have a proper rational function, then the horizontal asymptote is going to be at y equals 0. So anytime the degree of the numerator is smaller than the degree of the denominator, then the rational function is going to be proper. If the degrees are the same, then what you do is you take the coefficient of the first term in the numerator and divide it by the coefficient of the first term in the denominator, and that's going to give you your horizontal asymptote. It's always going to be y equals some number. But if the degree of the numerator is larger than the degree of the denominator, then you have to actually do long division in order to find the oblique asymptote if one exists. So if we look at this one right here, we have x minus 12 over 4x squared plus x plus 1. We know that the degree of the numerator is 1 and that the degree of the denominator is 2. So since 1 is less than 2, this one's proper. So the line y equals 0 is your horizontal asymptote. If we look at this one though, we have 8x squared minus x plus 2 over 4x squared minus 1. The degrees are the same, they're both 2. So in this case, what we do is we take the number that's in front of the x squared up top, which is 8, and the number that's in front of the x squared in the bottom, which is 4, and we divide those two numbers. So you say y equals 8 divided by 4, which just simplifies to y equals 2. So if the degrees are the same, you just divide the coefficients that are out front. Now, if you have something like this, where the degree of the numerator is 1 larger than the degree of the denominator, then you need to go ahead and do long division. If it's been a while since you've done this, I would suggest taking a look in your textbook and seeing exactly how to do this long division. But for this one, we get 3x plus 3. We end up with a remainder, but we just need to take that linear part. So this one's going to have an oblique asymptote at y equals 3x plus 3. Now, if the degree of the numerator is 2 larger than the degree of the denominator, then when you divide, you actually get a quadratic. So the graph of g is going to look like y equals 2x squared minus 1 as x approaches negative infinity or infinity. But since y equals 2x squared minus 1 is not linear, it's not oblique. So function g doesn't actually have a horizontal or an oblique asymptote. So here's a nice summary. This can be found in your textbook as well. But basically what you need to remember is that if your function is proper, so that the degree of the numerator is smaller than the degree of the denominator, then y equals 0 is going to be your horizontal asymptote. If the degrees are the same, then you divide the coefficients that are out front. If the degree of the numerator is 1 more than the degree of the denominator, then you're going to have an oblique asymptote, which is going to be found by dividing. And if the degree of the numerator is 2 or more greater than the degree of the denominator, then you're not going to have a horizontal nor an oblique asymptote, but you can divide to figure out what your graph will look like. So what I want to do is walk through 8 steps in graphing one rational function. I highly recommend that you go through your textbook. There are a lot of examples for this, and it's really important that you look at more than just one because these graphs can look a lot of different ways. So we only have, 40 minutes or an hour for this presentation, so I'm just going to go through one of them, but it's really important that you look at the others. So we're going to start with step 1, which in our case is going to be to factor the numerator and the denominator and find the domain. So this is always going to work. I would suggest doing a bunch of examples until you know these steps. But the first thing we're going to do is we're going to factor anything that we can. And in this case, we have the difference of 2 perfect squares in our denominator. So this one's going to factor. We're going to have r of x equals x minus 1 over x plus 2 times x minus 2. So if we set our denominator equal to 0, what we'll find is that we get x equals 2 and x equals negative 2. Those are the two numbers that we need to exclude. So because those are the two numbers that make our denominator 0. So the domain is going to be all x's such that x is not equal to negative 2 and x is not equal to 2. Now at this point, if there was any canceling that we could do, then we would go ahead and do that. And if something did cancel, then you would have a whole at that point. Again, I would go through the other textbook examples because there is one like that. But there aren't any common factors between the numerator and the denominator, so we can't cancel anything. So it's already in lowest terms. Step 3 is to go ahead and find the intercepts. So if we set x equal to 0, we're going to find the y-intercept. So if we set x equal to 0 and plug all of this stuff in, we're going to get 1/4 out for y. So we know that our y-intercept is going to be at 1/4. The x-intercepts are just the zeros of the numerator. So if you set x minus 1 equal to 0, you get x equals 1. That's going to be your only x-intercept. And then you can also find the behavior near 1 if you'd like. And this is using the same methodology that we used for the polynomials. We also want to locate the vertical asymptotes. So what we do is we set our denominator equal to 0 and we solve. We get x equals -2 or x equals 2. And then we want to locate any horizontal or oblique asymptotes. So if we look at this, if we set, or if we look at our degrees, sorry, we know that we have a degree of 1 in the numerator and a degree of 2 in the denominator. So this one's proper. So the line y equals 0 is going to be the horizontal asymptote. So if we want to determine if the graph intersects the horizontal asymptote, we would have to solve r of x equals to 0. All right, so now what we do is we use the zeros of the numerator and the denominator to divide into intervals. This is the exact same thing, so I'm not going to walk through this whole thing. But we have important points of -2, 1, and 2. -2 makes the denominator 0, 1 makes the numerator 0, and 2 makes the denominator 0. Then we write the intervals out, so we have 4 different intervals. We pick a number in each of those, evaluate, and then find a new point on the graph. So if we actually do this, we're going to have y equals 0. I would always suggest putting your asymptotes on there first. So we're going to have y equals 0. That's going to be a dotted line. That's going to be an asymptote. You are allowed to cross horizontal asymptotes. You cannot cross vertical ones. And then we're going to have vertical asymptotes at x equals -2 and x equals 2. At that point, I would suggest putting some of the extra points on there as well, like -3, -0.8. Our intercepts of 0, 1/4, and 1, 0, and then our other points here. And if we look, if we actually connect some of these points, what you'll see is that as x is getting closer and closer to 2, our y values are approaching infinity or negative infinity. That's why this is a vertical asymptote. And then as x is approaching infinity, we approach the line y equals 0. And as x approaches negative infinity, we also approach the line y equals 0. So that is why this is also a horizontal asymptote. So like I said, it's really important to go ahead and review a bunch of those examples. You're going to walk through the same kind of idea each time, same set of 8 steps, but it's really important that you do a lot of practice. They're quite difficult to graph and they take a lot of time to grasp. But please email me if you have any questions. Again, my email is pseeburger@ivytech.edu. That's pseeburger, like burger as in the food, at ivytech.edu. Thanks for listening.